Okay, so welcome to the second semester. I will be your instructor for this semester, so let me start by introducing myself. This is my name. I'm on the fourth floor in this department, in the room 426. I usually don't tend to have fixed office hours, but whenever you have a question, just drop by. If I am free, we will discuss. So don't wait for an office hour. I was hoping to put an office hour on Monday right after the lecture. Since you are already here, if you have any questions, we could discuss, but unfortunately, I had some other lectures afterwards. But I might try to put an office hour the hour before so that you can come here when you have questions and then we can continue with the lecture. And my email address So if you have questions, if you cannot come to my office or if you fail to find me in my office, send me an email. We can either try to solve your problem through email. If not, we can arrange a time and meet for your questions. And I'm a particle physicist. Well, mainly my specialty, even in particle physics, is what we call the hadronic physics. You have probably heard of the Large Hadron Collider. That hadron. It's basically like the proton and neutron, anything that is made up of quarks we call hadrons, and I'm just trying to understand their properties. So if you have any questions on particle physics, just feel free to drop by my office. And this semester we will be studying with you electromagnetism. Well, you are probably already familiar from last semester in mechanics. We again go just step by step from the most simple to the more complicated. And we will be using the concepts that you have learned in the last semester. So if you have trouble remembering them, I would strongly advise you to go over them. What is force? What do we mean by energy, etc. So those concepts are some concepts that we will be using frequently also in this semester. Now, we will be discussing electricity, and we will start with charges at rest. So what we call electrostatics. Then we will continue with charges moving at constant speeds. Well, we won't be studying all the possible charges moving at constant speed, but what we will be studying is currents running through wires. We will see that such currents create another force, what we call the magnetic force, and the study is called magnetostatics. These are systems. They are static in the sense that the magnetic field doesn't change with time. Electrostatic is static in the sense that the electric field doesn't change in time. And then once we discuss electrostatics and magnetostatics, then we will continue with dynamics. Basically, what happens when the magnetic field is changing. And that will be the end of the semester. Now, any questions? Anything you are curious about? I have one suggestion to you. I suggest all my students to watch this video. By Eric Mazur. Well, it's 1 hour and 1.5 hours long. It is fun to watch. I mean, I was meeting with a professor from some other department yesterday. She was from the biology education, and she was just complaining that all her nightmares about the physics just arose due to her visit to the department. So physics is somewhat fearsome for non-physicists, at least. Even for physics students, they usually perceive physics as fearsome. So what Eric Mazur does, he's a physicist in Harvard, a condensed matter physicist, and he's also interested in physics education, in general education, in particular physics education, and he's trying to come up with ways of improving the education. And one conclusion he has is that as long as we just carry out standard lectures, meaning that I speak, you listen, and at the end you don't learn anything, I cannot teach anything. So we are just wasting 3 hours a week here, just you listening to me. So if you would like to learn, I would ask you to participate. Ask questions, interrupt me whenever you feel like, ask when you don't understand anything, ask questions. I mean, in such large classrooms, one advantage is that there is almost always at least 1 or 2 students who ask so-called stupid questions. But at the end of the day, thanks to those stupid questions asked by that student in the class, all of you start learning. And, well, if you have stupid questions especially, please don't hesitate to ask. So they are most of the time the greatest questions I have heard. And they always start with, I know it's a stupid question, but I mean, those questions are the greatest ones. Okay, some participation, some feedback to me, yes or no? Has anyone seen an electron?
Not an electron, not an electron, but a bunch of them.
Where?
When when you're jumping on a trampoline, for example, and touch someone, and there's a shock.
Okay, anybody else? Okay, you have seen a current. Well, I'm sure you all have seen an electron. This is an electron in Greek. So this amber in English is called electron in Greek, so that's where the name comes from. So basically, the origin of the phenomena of electricity kind of started with this amber. So what people observed was when they rubbed cloth on amber or glass, there was something going on. So it could create shocks, it could attract other objects, and so they should give a name, so they chose the name electron, electricity from the electron. Now, we will be studying various kinds of electrons. The first one we will study will be a static charge. So as physicists, we are not just happy, oh, nice, there's a shock over there and story there, but we would like to study it, we would like to describe it, we would like to make predictions about it. So you see this phenomena, amber plus cloth, you get some weird phenomena. So what would you do next? If you were there, you didn't know anything about electricity, but you had somehow rubbed some cloth on amber, and you have seen that, let's say, it attracts very small pieces of paper or very small objects, then what would you do next?
Find out what was going on.
So, what do you do?
Trying to do some research.
What do you mean by you do? Okay, you will do some research, great, but what does it mean to do research? Yeah, different materials. But without any with just this observation, you cannot really come up with hypotheses or theories. You need more experimental evidence. You need some more phenomena. You have to have many different observations so that to explain all these observations, you come up with certain hypotheses, and then you create your theory from that hypothesis. So what you do is, okay, so what other experimental observations would you try? Okay, experimentation is mainly changing certain parameters in your experiment. So here we have one experiment, amber plus cloth. You have some phenomena. What can you change in your setup? You can change amber, for example, or you can change cloth. You just try different materials. You rub it on glass. You rub cloth on glass. You rub cloth on wood, cloth on, I don't know, some metal, or amber on. You just make all your combinations and then try to understand this phenomenon, what's going on. Well, one observation was that essentially if you have, let's say, you create a glass, you rub cloth on glass, and then you rub amber on glass and bring it to, amber on cloth and bring it here. There's an attraction. Then you change, you have the glass, and you create another glass. There's a repulsion. So what can you conclude from these?
Like charges repel.
Like charges? What do you mean by charges? I didn't yet define charges.
Like charges.
So what do you mean by charges? What does it mean to be like charges? Eventually we will reach there. But you see, you don't know what charges are. You haven't seen electricity. You didn't take a general physics course yet. So what does it mean to be like charges? You don't know. But in a sense, like materials repel each other. Different materials attract each other. This is your hypothesis. Well, then you keep changing your materials, and then you discover that there are other materials which repel glass. Okay, you had one hypothesis. You said that, okay, same materials repel, different materials attract. This was your hypothesis. But then you tried other materials, and you found some other material except than glass, which repelled glass. So your hypothesis is kind of disproven.
Like the cloth that we rub the amber with. Keep it closer to the glass, it will be better.
The amber, well,
The cloth that we use to rub
the cloth and the amber, they will attract each other.
No, I'm talking about this cloth with the glass.
Oh, that cloth. Okay, yes. So you are saying that we have the glass, we also rub the cloth on amber, and when we bring the amber, there is an attraction. When we bring the cloth, there is a repulsion. So it's not just like materials, but as you said, there should be some other property which will tell me that whether it will attract or repel. Well, it turns out that with such experiments, there are only two different kinds of these things. So if you have two things, you can call them 1, 2, or AB, or plus or minus. And that was the convention. So the convention was the charge of glass is defined to be positive. This is defined as positive. And this is the other charge which attracts the plus charge is negative. So why is it positive? Why is it negative? I think it's probably Benjamin Franklin who liked the glass more. So he wanted to call it positive. So it doesn't really make any difference. Somebody else could have called the charge on glass to be negative. So this is kind of the origin. Okay, so now you have this force. What would you do with this force? What would you like to know about this force? Okay, we have discovered that there is this additional force. At least it attracts some small pieces of paper. You can try it with a comb. There is this force. It exists. What else would you like to know about this force? The strength, the magnitude of the force. What else would you like to know? Its direction. Because you already have studied Newton's dynamics. Newton's dynamics tells you that if you know the forces acting on objects, you know what it will do, how it will move. So, but knowing the force, being a vector quantity, force has two properties. It has a magnitude and it has a direction. If you don't know any one of these, then you don't really know the force. Now, it also turned out that there are certain materials, metals in particular. Let's say you have a metal, positively charged. Now, you can test whether it is charged or not by just bringing it close to a glass that is already charged. So if it is repelling the glass, then you know that the sphere is positively charged. If it is attracting, then it is negatively charged. And then if you bring another one next to it, a neutral one, and make them touch. If you connect them and then separate them, you will see that both are now charged. So this phenomena this is a way, okay, one method of charging objects was rubbing some kind of a cloth on them. Now, this is another kind of charging the objects. So you just well, it doesn't work on every material, but it works on metals. If you just bring them in contact, some of the charge is transferred to the other one. So this is called conduction. So if you realize that there is such a phenomena, well, you would like to know which materials have these properties. So you just make experiments. So this one, you can try, let's say you have a charged sphere, and take another metal object and put on top. And what happens is, again, both spheres become charged. If this is metal, well, all of them are metals. If you bring wood, then, well, the second sphere is not charged. It stays neutral. If you bring, what else would you like to try? Plastic bottle. Again, nothing happens. Well, so coins, you put a coin on top. It's a metal. And you realize that you can classify objects, any object, as either a conductor, which allows transfer of charge, or insulator, which does not allow the transfer of charge. Well, it turns out that there are other ways of charging the objects. For example, you know that metals can be charged. They are conductors. So let's say you have a charged sphere. You bring another charged sphere, but take a wire and put it in contact with the ground, some water, humid place on Earth. And so after this experiment, you realize that, and then you bring it, you have this conductor, another conductor, a charged conductor, or any charged object, doesn't have to be a conductor. You bring it close to this one, connect it to the ground, and you just cut the connection to the ground, and remove this thing, and at the end you would have a charged conductor, which happens to be negatively charged. So in difference from the previous cases, this is by conduction. You see, after conduction, both spheres have the same charge. In the other case, what happens is the charged object now has the opposite charge, and they have never been in contact. They have been in the close proximity of each other, near each other, but they have never been in contact. So this is called by induction. Now, of course, we know that charge exists. The next thing we would like to know is what about how do we measure the charge? And the unit of charge is Coulomb. Now, this was, of course, the idea of Coulomb was before people really understood what was going on inside the material. We didn't know about the electrons, we didn't know about the atoms, we didn't know anything about the internal structure, basically. But what turned out was, at the end, now at least, we know that everything, all the materials, well, in your department you will be studying many materials, all the materials are made up of atoms. So if you take any material, inside you have many atoms, and atoms are essentially, you have a nucleus which is positively charged, and around this nucleus we have electrons, which are negatively charged. And the charge of an electron is defined as minus E, where E is a constant times 10 to the power minus 19 coulombs. So the charge of an electron is quite small. So if you go back to all the previous observations, what we know, if you just pick up any material, like this one, like glass or amber or cloth, they're all made up of electrons and nuclei. When you rub them one onto the other one, it might happen that, well, the nuclei are quite heavy. They are most of the time fixed where they are. But the electrons have more freedom. They are already moving very fast inside your materials. So what happens is when you rub them on each other, some of the electrons will be transferred from one material to the other one. So the material that has more electrons than protons, it will be negatively charged. And if the object that loses electrons, so it will have more positive charge than negative charge, it will be, if you just sum all the charges, it will be positively charged. So this rubbing by charging by friction is basically the transfer of electrons from one material to the other material. Well, how do you determine in which, you are just rubbing cloth to amber. Why doesn't the electrons go from amber to cloth, or why do they go from, why do the electrons go from cloth to amber? Well, it's basically determined by the properties of your materials. So some materials are stronger at attracting electrons. Some other materials are less strong. So if you just rub those two objects, it's more likely to go from the material that attracts the electrons less to the material that attracts it more. Well, if you look at what is a conductor and an insulator, well, the main difference between the conductor and an insulator is in an insulator, the charges are fixed where they are. If you pick up this book, This is made up of atoms. And the atoms have electrons, but electrons are very tightly bound to their nuclei. They cannot leave their atoms. So they are always fixed. But other materials, like metals, a very simple picture of a metal is electrons moving around freely on the background of uniform positive charge. So you just imagine that you have a uniform positive charge distributed, fixed, and the electrons are just free to move within this system. And within this system, they can just go from anywhere to a different part. So, for example, if you look at this picture, what happens when you bring the coin in touch with this conductor is that this conductor has more positive charges than negative charges. The coin has positive and negative charges. Well, there are more negative charges here, so the electrons will be attracted here. So the electrons will move here. But if the electron moves from coin to the conductor, what will happen is the coin will be charged positively. But the positive charge of the coin will attract some charges, negative charges, electrons from the other sphere. So at the end, electrons will move from coin to this sphere, and then some other electrons will move from this sphere to the coin. And at the end, this sphere will lose electrons. That is why it becomes positively charged. This sphere will gain some electrons, so that's why its charge will be reduced. Here we had more charge than here. Well, of course, the coin, depending on its size, it will also keep some charge, but at least in this sketch, I'm just assuming that it's so small that the charge it contains is very small. And once the electrons are moving in this direction, this sphere will also be positively charged now. This sphere is positively charged. Both of them will try to attract electrons, but so they will be balanced. The flow will stop. So in this, at least in this electron picture, the dynamics going on in this charging by conduction is that you have the flow of electrons. Well, similarly, in this induction, you still have the same flow of electrons, but in this case, what happens is you bring a positive charge close to a conductor. The electrons are free to move. There they see a positive charge, so the electrons will move towards the positive charge. Since there is no contact, they will not be able to go to the sphere, but they will stay here. There will be more negative charges over here than on the other side. So if there were no such wire, the electrons will move from here to there. So this end will be charged positively because there will be less electrons here than here. So this end will be positively charged, this end will be negatively charged. The whole object as a whole would be neutral. So once you remove this sphere without this wire, the whole thing, negative charges and positive charges will combine. So it will neutralize everywhere. So the object as a whole will be neutral. But if you put this wire, so-called, if you ground this end, well, the electrons will move towards this end due to this positive sphere. So there will be less electrons here, but there will be more positive charges. Those positive charges will attract some electrons from the ground. So the electrons will move from the ground to this end, neutralizing the positive charges. Of course, the Earth will be somewhat positively charged because it has lost electrons, but Earth is so huge. I mean, just attracting some electrons wouldn't make any difference for Earth. So any questions up to this point?
Is the material in contact with Earth, does it make any difference when we press something? So if we're on asphalt and we have a wire touching Earth, does that have any difference than if it was rock or wood or whatever?
Well, it will have some difference. The thing is, whatever it is touching should be a conductor. So at the end of the day, if you want to use Earth as your ground, whatever charge you give to the ground, it should go away.
But rocks and asphalt, for example, are not conductors. Not good conductors.
They are not good conductors, so they don't make good grounds. Usually what is conducting on Earth is water. or salts solved in water actually. You see, although in metals, the charge is always carried by the electrons, it doesn't have to be so. So if you have an ionic solution, like if you put some salt in pure water, is a really bad conductor. But if you put some salt to it, it becomes a good conductor. Because what happens is when you prepare this salt solution, the salt is sodium ions plus chlorine ions. An ion is an atom that has lost or an electron or gained some electrons. So it becomes positive or negative. The sodium becomes positively charged. Salt is sodium chloride. So sodium is positively charged, chlorine is negatively charged. If you prepare a salt solution, you have many positive charges, many negative charges. They are just free to move around inside the liquid. So the solution becomes a good conductor. So if you just bring a negatively charged object here, a positively charged object over here. So negative charges, the chlorine ions will move in that direction, and the sodium ions will move in this direction. Now, salt is everywhere on Earth. Water is also quite common. So if the humid Earth is a better conductor than a dry one. A rock is not such a great conductor. But if you think, even air is a conductor, especially if it's humid. You see, suppose you take your comb, especially if you have long hair, when you are combing your hair, you might have realized that after some time, especially with certain combs, it's hard to put it in a nice shape. Whenever you approach to comb to your hair just stands up. You probably don't see it with your curly hair, but your friend next to it probably is witnessing this phenomena. And when you comb your hair, trying to straighten it, you end up having with all these strings going up. You probably see it, you also see it. You might also see the same phenomena. So that's basically static electricity building on your hair. But at the end of the day, if you wait for some time, it just disappears. Where does it go? Basically, it goes to air. And in the air, again, it's due to it is due to the humidity. Because when you look at the water molecules, there are two hydrogens, one oxygen. Although the molecule as a whole is neutral, the hydrogen side is slightly positive, the oxygen side is slightly negative. Since there are various charges at different points, these ends, they can easily acquire an electron. So if your hair has excessive electrons, the water molecule can take it away. Or if it has lost electrons, again, it can easily give one electron to your hair, so it just goes down. Another way to get your hair down is just use a sharp metallic object. It also works. And, well, another thing that we know about these charges are conserved. Well, charge conservation is nothing but conservation of the total number of electrons and protons in a material. At least through everyday processes, we cannot create electrons, we cannot destroy electrons or protons. So their number is fixed. Since their number is fixed and the charge is determined by their number, the charge of an object is always conserved. It just moves from one point to the other point. Nowadays, with the accelerators, we can create electrons and protons from energy, but even in that case, the charge is still conserved. So if you create a negatively charged electron, at the same time you create a positively charged electron, so-called the positron. So we know nowadays that whatever happens, charge is a quantity that is always conserved. Okay, any questions about this qualitative discussion? Now comes the formulas. Okay, so at least now we have qualitatively what is going on. We had said that we want to know the forces. So we have some charges around. How much force do they exert on each other? That is something we would like to know. And again, I think it was the Coulomb who did many experiments with charges. And he discovered that the force, the magnitude of the force, was proportional to the charges, the product of the charges. You see, if you think if you put yourself in the shoes of Coulomb, you don't know about the charges, you don't know anything about the electrons, etc. You don't have any means of measuring the strength of charges. So how can you determine that the force should be proportional to the product of the charges? I mean, if you can measure the charges, the magnitude of the charges, then it will be kind of easy. Just put some charge, double the charge, triple the charge, and measure it. But how do you double, triple the charges? Okay, that is another thing. I mean, the complete expression will be it is proportional to the product of the charges and inversely proportional to the distance squared. Now, this is also easy experimentally to determine. You just take two charges, measure the force they exert on each other, change their distance, and see how the force changes. So then you can determine this 1 over r squared behavior. But the dependence on the charges itself, I would say that's quite difficult without having any means of measuring charge itself.
We can use conduction. So, for example, if we have a ball that's charged, then we bring the same material ball, and then we connect them together. Then each one of them will have half the original charge.
That's basically what the Coulomb did. Great. So the idea is you start with a charged sphere. You charge it somehow. Although you cannot measure the charge, you know that it has some charge, let's say Q. Then you bring another identical sphere, bring it in contact, and then separate them. At the end, what you have is you have a sphere with charge Q over 2 and another sphere with charge Q over 2. Well, since the two spheres are identical, there is no reason for one of them to have more charge than the other one. So since they are identical, they should divide, whatever the mechanism is, they should divide equally. And then you bring a third one. Bring it in contact with one of these spheres and then separate them. So after this step, you have a sphere with charge Q over 2, another sphere with charge Q over 4, and a third sphere with charge Q over 4. You don't know what their magnitude are, but you know that their ratio is 2 to 1 to 1. Then you bring a fourth one. Bring it in contact and then separate them, and at the end you have 4 charges. Q over 8 and Q over 8. And so on. So you can basically create different spheres, or identical spheres with different charges. And you also know the ratio of the charges. So then you can just go ahead and, let's say, measure the force between these two at a given distance. If you know the force, then compare it with the force between these two at the same distance. So the distance doesn't play any role. So what you would discover is how much would the force change if you just calculate the force between these two and then these two. How much will the force change? By half. One of the charges is fixed. The other charge is halved. The distance is the same. So if you observe that the force between these two objects is twice the force between these two spheres, you would be tempted to say that it is twice, at least the force is proportional to the charge of this one. And then you can also compare it with these two. Well, you just repeat the step, obtain a sphere with charge Q over 16, and see that with every different sphere, the force is reduced by a factor of 2. Then you would conclude that the force should be proportional to the charge of one of them at least. Well, they are basically symmetrical. So if the force is proportional to the charge of this sphere, somebody else could bring this one over here and this one over here. The force will be identical. So if it is proportional to one of them, it should be proportional to the product of both of them. So then you have this force law. The force is equal to the product of the charges divided by the distance squared. Well, the experiment can tell you by comparing the magnitudes with in different experiments, you can find the proportionality constant. Then there's the proportionality rule, but then to convert it to an equality, there's a proportionality constant, the K. So this is our force law, the magnitude of the force. And then, of course, the direction, also the direction turns out to be along the line connecting the charges. If this is Q1, this is Q2. It is along this line. If Q1 and Q2 are identical charges, it will be pointing away from each other. This is the force exerted on 1 due to 2. This is the force exerted on 2 due to 1. And they have the same magnitude. And R is this distance over here. Keep in mind that this law, this Coulomb's law, is valid only for point objects. So this is valid only if these two are points. They are not, it's not valid if you have extended objects. They are not valid for these spheres. They are not strictly valid, but approximately even for those spheres it will be valid, especially if the spheres are much smaller than their separation. Any questions?
Does this relation hold for non-uniform objects? Does this relation hold for non-uniform objects?
Well, you see, this relation holds only for point objects.
Yeah.
Point objects, I mean, it doesn't make sense to talk about non-uniform point objects.
No, I'm talking about like everyday objects. How do we calculate?
We will see that. We will see that. Can we use this for extended objects, large objects? We will study it. Well, let me ask you another question. The electrostatic force, we said that this is K Q1 Q2 over R squared. You have already seen the Newton's gravitational law. This is the Newton's constant M1 M2 over R squared. The law is almost identical. Both of them are proportional to the product of two properties of the materials. Both of them are inversely proportional with R squared. Well, there's a proportionality constant, which depends on the units you use. Well, there is one important difference. The gravitational force is always attractive, whereas the electric force is always repulsive. Now, sometimes repulsive, sometimes attractive. But why is the R squared? Why are they the same? Okay, this is for you to think about. We will come to this point later on. Any questions before you go for a break? Okay, see you after 10 minutes.